I want to take a look at the area of a sector of a triangle. Um, this isn't really trigonometry here, it's just relating of angles and arc lengths and circles and such. So here we go. A sector of a circle is a piece of pizza. It's a pizza pie or a piece of pizza pie. It's a wedge from the game Trivial Pursuit. Lots of different ways you can think of this sector. You got the center of the circle here. You got an angle at it, so it's got two lines coming out. Each one, of course, is the radius, and you got an arc length that's cut off. So this right in here is this. Actually, let's color it in. Let's pick something like red. Right? So I'm going to be trying to find the area inside this sector here. There's a couple ways to think of this. One is, if you think of this as being a fraction of the circle, you could say, well, I know the area of the whole circle, right? The circle area is pi times the radius squared. You say, well, what fraction of that whole thing do I have? Well, all the way around would be 2 pi radians, and I've got theta radians right here. So the fraction that I have is fraction of the circle is theta divided by 2 pi. 2 pi would tell me all the way around, and I'm just saying, well, how much of that do I have? What fraction do I have? That's also the fraction of the area that I have. So the sector area is the total area times the fraction of the circle that you have. I can simplify things a little bit. The pi's cancel out. I end up with 1/2 r squared theta. Right? And this is a fairly common way to think of this. So if you know the angle and you know the radius, you can find the area. Okay. One thing I want to look at, though, is I view this a little bit differently in that sometimes I view this sector, I like to put it this way. Got this angle theta here, this radius r right there. This is also radius r. We just learned about arc length. So how long is that arc length? If you know the angle and you know the radius, well, the arc length is the radius times the angle. Right? Everything's done in radians here. And then I look at that and say, well, that kind of looks like a triangle. And I know that the area of a triangle, area of a triangle is 1/2 the base times the height, right? Well, I'm going to think of this way, where the base here is the arc along the bottom, and the height is, well, drop a perpendicular, right? Well, the funny thing is, this is the arc of a circle, and so that perpendicular is the same length as this side over here, so this has length r. But let's just see. If I think of that as a triangle, and I say 1/2 the length of the base, that's the length of the base, times the height, I end up with 1/2 r squared theta, which is exactly the same thing that I had up there. That somehow this sector is behaving like a triangle. That is, if I thought of this as, if I view this now as say a bunch of concentric circles, all having this as a center, think about all those arcs. And what I'm going to do is I'm going to take those arcs, here I still have this r right here, and I'm going to stretch this one out here on the bottom, which is the same length as r theta. So this one's curved, this one's straight, and all these other ones I just keep straightening out. Right. And what I'm going to end up with is a triangle. Right. If I sketch that in the same spot, let's do it in like green here. That is, when I unroll that red thing out like this, it's going to unroll like that, and then this would come down in here, and this would come down in here. And it turns out that if you compare the sector and the triangle, that there'll be some little bit of area down here that's in the triangle but not in the sector. But then there'll be these wedges on the sides that are in the sector but aren't in the triangle. And it turns out that these balance off exactly, and that the area of that sector is the same as the area of this triangle. Which leads for an interesting way of thinking about the area of a circle. Because if I think of a circle, and I want to know, let's say it has a radius here, I want to think of this as a triangle. I want to take that whole circumference and unroll it into a triangle. So take that whole circumference and unroll it. So this is a whole 2 pi times r, all that circumference all the way around. Now this is going to be my perpendicular, dropped from here straight down there. So there's my height, and everything unrolls like that. If you think about a bunch of concentric circles, right, open up each one of those circles into a straight line, right, until it opens up into a triangle. What's the area of this triangle? The height of the triangle is the same as the radius of the circle right there. So the area is 1/2 times the base is 2 pi r, times the height of r, for a grand total of the 2's cancel out, and I get pi times the radius squared. Wow. Is that a circle or is it a triangle? Well, it turns out that they're very, very closely related. Someday when you get to Calc 4, we'll look at the transformation of the plane from here to there and show that the Jacobian is equal to 1, whatever the heck that means, right? But because the Jacobian is 1, this transformation doesn't change the area. It really is. The area of the circle is the same as the area of this triangle. Fascinating little bit of geometry.